Hello everyone, my name is Sooryansh Asthana and today I am going to present before you our work on interrelation between non-classicality features through stabilizer group homomorphism. So the outline of the talk is as shown in the slide. First I will talk about the motivation underlying the work. Then I will give a brief introduction of homomorphism between stabilizer groups, and then I will show how condition for coherence give rise to entanglement and non-locality themselves if one looks at the homomorphic images of suitable stabilizer groups, and then I will talk about the conclusion and future scope of the work. So, as we know that there are many criteria for non-classicality, for example, quantum coherence, quantum entanglement, non-locality, etc., and they have been motivated by different aspects. For example, in quantum entanglement, separability is the notion of classicality. In non-locality, there is a locality hypothesis which does not take recourse to any underlying Hilbert space. So, but one thing we know that within the domain of quantum mechanics, in some sense, coherence underlies all of them. So, it is a natural expectation that all the criteria for non-classicality should emerge from the ones for coherence. So, we will illustrate it through the stabilizer group homomorphism for the case of multi-qubit systems. So, the preliminaries which are required for the talk are number one, the stabilizer group of a state. So, as shown on the slide, the stabilizer group of a state is a group that leaves the state unchanged. So, as an example, the set of rotation. Suppose there is an axis n hat like this, and the set of rotation about this axis n hat stabilizes this axis of rotation, and the multiplicative group identity and Pauli matrix X stabilizes the state 1 over root 2 0 plus 1, and these are some examples that we will use later on in the talk. The multiplicative group of Pauli matrices identity x1 x2 minus y1 y2 and z1 z2, they are stabilizer group of 2 qubit Bell state 0 0 plus 1 1, and this is the stabilizer group of GHZ state 0 0 0 plus 1 1 1. The last two stabilizer groups are isomorphic to Z2 cross Z2 and Z2 cross Z2 cross Z2 respectively. So where Z2 is the group of addition modulo, group of integers addition modulo 2. So that is the thing. Now homomorphism between different groups. So a group homomorphism is a map that preserves the group multiplication, as is shown here, that if A maps to alpha and B maps to beta under some map, so A star B maps to alpha dot beta. The group multiplication may be different in the two groups, but the point is that A star B will map to alpha dot beta in the group G prime. So as an example, if we take the group of stabilizers of 2 qubit Bell state and look at its homomorphism with the group of stabilizer of the single qubit state 1 over root 2 0 plus 1. So as is shown here, this identity and x1 x2 map to 2 cross 2 identity, and this is the coset minus y1 y2 and z1 z2 which maps to Pauli matrix X, and it can be verified that it is a homomorphic map because it preserves the multiplication of. So some terminology that we will need throughout the talk is number one is coherence witness. So as is known that any non-classicality witness is an operator if and that operator satisfies these conditions, that the expectation value of that operator is greater than or equal to 0 for all these states which do not possess that non-classicality feature, and there exists at least one state for which the expectation value of that operator turns negative. So for the special case of coherence, any operator O is termed as a coherence witness if expectation value of O is greater than or equal to 0 for all incoherent states, and it is less than 0 for at least one coherent state. So the example is expectation value of X bounded by half. So this operator takes non-negative values for all the states which are incoherent in the eigenbasis of the operator sigma z, and the states which are coherent in the eigenbasis of sigma z, for some of them it has a negative eigenvalue. For example, this 1 over root 2 0 plus 1. So for that its value is 1, the expectation value of x is 1, so that is why this condition is violated. So the next concept that we will need is that of entanglement witness. So any operator O is termed as an entanglement witness if the following two conditions are satisfied. So again the same thing, but here since the notion of classicality is separability, so expectation value of O hat is greater than or equal to 0 for all separable states, and expectation value of O is less than 0 for at least one entangled state. So as an example, this is the optimal linear witness for two qubits x1 x2 plus y1 y2 plus z1 z2 bounded by 1. So the last thing that we will need is non-locality inequalities, which are quite well known. So they are inequalities which are satisfied by all local hidden variable models of the type I have given here an example. For example, if there is a bipartite system and A is an observable acting over the space of first subsystem and B acting over the space of the second subsystem. So P probability of the outcome small a of the observable A and outcome small b of the observable capital B. If this probability can be written as a weighted sum over the conditional probability of observable A taking value small a given lambda and observable B taking value small b given lambda, where lambda is known as local hidden variable and rho lambda is its probability distribution. So if this joint probability P A is equal to A, B is equal to B, this can be written in the sort, then this is one kind of local hidden variable model. And if there are inequalities which are satisfied by all the local hidden variable models and violated by at least one quantum mechanical state, so they are called non-locality inequalities, and one prime example is CHSH inequality. Now after this we will come to the central theme which will be required, so that is homomorphism between stabilizer groups. So this is the observation that we have made, that multi-qubit stabilizer groups have such a homomorphic mapping with single qubit stabilizer group that does not allow for consistent assignment with a local hidden variable model. So what do we mean to say by this? So let us take an example. If we take an example of a stabilizer group of a qubit and that of a 3 qubit GHZ state. So stabilizer group of a single qubit 1 over root 2 0 plus 1 is identity and Pauli matrix X, and that of 3 qubit GHZ state is an 8 element group which we have written here. So now if we take a homomorphic map, so this is the kernel of homomorphism, identity z1 z2 z2 z3 and z1 z3, and this thing is a coset. So now in this coset the point is which maps to a Pauli X operator acting on a single qubit. So these are the operators which do not allow for consistent assignment of local hidden variable values or some joint probability scheme, and these are exactly the observables which have been used by Mermin for construction of his celebrated non-locality inequality for a 3 qubit system. So this is the inequality that any local hidden variable model gives a maximum value of 2 for this operator. And why is it that? Because if we multiply all the four terms x1 x2 x3 minus x1 y2 y3 minus y1 x2 y3 and minus y1 y2 x3, so the product of all these four terms is equal to minus 1. So this means that if these values have to be consistent with a local hidden variable model, then three of them should be of the same sign, and the fourth one should be of a different sign. So the possible values are -1, -1, -1, and +1, or it is the other way around, 1, 1, 1, -1. So the point is that for any such choice, the maximum value is bounded by 2. But we know that 3 qubit GHZ state gives a value of 4 for this operator. So this is the this observation we will use throughout our work, that so we will start with a group of a single qubit thing, and we will look at its we will go to higher number of qubits, and then we will try to build a homomorphism and try to look at the inequality that follows. So the implication of this thing is that a systematic study of homomorphic mappings of stabilizer groups of n qubit states to those of n qubit states where m is less than n may lead to various non-classicality inequalities for different non-classical aspects. So this is the point, that we will do a systematic study of homomorphic mappings of stabilizer groups of m qubit states to those of n qubit states. So the first thing that we are going to show is that under this homomorphism, condition for coherence gives rise to condition for non-locality, and thereafter condition for coherence gives rise to condition for entanglement. So we start with the coherence witness that I have shown as an example earlier. So this coherence witness expectation value of x is bounded between 0 and half, and this gets mapped to this entanglement witness x1 x2 minus y1 y2 bounded by 1 under the homomorphic map. This x1 x2 minus y1 y2 maps to x. And similarly, if we also look at the third Z1 Z2 operator, then this coherence witness expectation value of x is bounded between 0 and half. This maps to this entanglement inequality, which is the optimal entanglement inequality for 2 qubit systems, as follows. So expectation value of x is bounded by half, and we will employ this map, this homomorphic map, that x1 x2 comma y1 y2, this maps to Pauli x operator, and identity and minus z1 z2, they map to identity operator. So we will use these things here, and 1 minus 2 expectation value of x, this thing goes to this optimal entanglement witness, optimal linear entanglement witness for 2 qubit systems. And we believe that this is attributable to the fact that when we look at as a whole, the entanglement in a 2 qubit system is nothing but coherence when the 2 qubits are looked upon as a whole. Similarly, if we look at the coherence witness expectation value of x is bounded by half, and we look at the homomorphic map of this thing, this x, for the stabilizer group of 3 qubit GHZ state. So this maps to nothing but Mermin's inequality. So, and this procedure admits a straightforward generalization to higher number of parties. After that, we start with the entanglement inequalities for 2 qubit systems straight away. This optimal entanglement inequality, x1 x2 plus y1 y2 plus z1 z2 bounded by 1, and we employ this homomorphic map in which x1 x2 x3 minus x1 y2 y3 map to x1 x2, and other two mappings have also been shown here. So this is the stabilizer group of GHZ state, which is on the left, and this is the stabilizer group of Bell state, which is on the right. And when we imply this homomorphic map, this is the inequality that we get. So this is the non-locality inequality. The local hidden variable bound is 4, because this the first two terms which contain x1 and y1, their sum is bounded by 2, and the 2 comes from this these two terms. So the local hidden variable bound is 4, whereas the quantum mechanical value is equal to 6, which is obtained for 3 qubit GHZ state. So generically, if we treat a1, a2, a3, and a prime, a2 prime, A3 prime as some dichotomic observables, so acting over the spaces of first, second and third qubits. So then this inequality can be written in this form, and now these A1 AIs, A prime I's and A double prime I's may be any dichotomic observables, not restricted to just Pauli observables. So, so far we have looked at only the linear entanglement inequalities and linear non-locality inequalities. Now we move on to non-linear entanglement inequality. So this we know that this is a non-linear entanglement inequality for a two-qubit system, and we imply the homomorphic map of single qubit operators x, y, and z through three qubit operators to arrive at this non-locality inequality, and the local hidden variable bound is 32. Now we turn our attention to getting CHSH inequality from coherence witness. So now this thing that we take this coherence witness expectation value of x is bounded by 1 over root 2, and this maps to under the homomorphism which we have discussed earlier, this x1 x2 minus y1 y2 bounded by root 2, which can be written as a1 plus a1 prime a2 plus a1 minus a1 prime a2 prime bounded by 2 for specific choices of a1 a1 prime and a2 a2 prime. Now there is a natural question that emerges: why this choice of 1 over root 2? So the answer to that is that expectation value of x bounded by half will detect more coherent states, meaning the less coherent states are also detected, whereas this thing will detect as comparison to in comparison to expectation value of x bounded by half less number of coherent state, and the coherent state which are detected are relatively more coherent. So the point is that more stringent coherence witness gives rise to non-locality inequalities, and less stringent coherence witnesses give rise to entanglement inequalities. So in conclusion, we have studied the interrelation of various non-classical features, for example entanglement, non-locality and coherence in systems having different number of qubits, and we have shown that inequalities for coherence themselves map to conditions for entanglement, non-locality, etc. under suitable mappings. The features that we have observed is that for two qubits, a more stringent coherence witness gives rise to non-locality inequality, and a less stringent coherence witness gives rise to entanglement inequality. And a single coherence witness maps to entanglement and non-locality inequalities when the number of qubits is increased. So we want to thank Professor Ravi Shankar for explaining the physical implication of this work apart from a pure mathematical equivalence of logical qubits, and Rajni Bala for many discussions and insightful comments. Thank you, and if you have any question, then my email ID is there, and we can discuss. Thank you.